I wanted to work through a problem or solve a problem that involves electric fields and involves the superposition, the summing of electrical fields due to several different charges. So in this problem, we have 3-point charges. I labeled them Q1 and Q2 and Q3. And those 3-point charges are arranged at 3 different locations on the arc of a circle. And the radius of the circle, we're told, is 4 centimeters. And we're asked to figure out the resulting total net electrical field at the center of the circle. And so we've got to superimpose, using superposition principle, the electrical field of the 3 individual charges to get the total electrical field of the 3 charges at the circle's center. So here in this diagram is the arrangement that we're thinking about. Charge Q1 above the horizontal axis, Q3 below the horizontal axis, Q2 on the horizontal axis. The sizes are 3 nanocoulombs for Q1 and Q3 and -2 nanocoulombs for Q2. They're each 4 centimeters from the center of the circle. And as you see in this arrangement, Q2 is horizontally to the left from the center of the circle. And Q1 and Q3 are 30 degrees above, 30 degrees below the horizontal. So these 3 charges are each going to make an electrical field. They're individual electrical fields at the location of the center of the circle. And the first thing I'm going to do is sketch those 3 electrical fields. So let me go ahead and do that. So Q1 is positive. The field points away from the charge. Here's a little field vector representing that field. I'll label it E1. Q3 is also a positive charge. The field points away from the positive charge, and I'm going to label that electric field vector Q E3. And then finally, Q2, that's a negative charge. And so the field lines will point towards that charge Q2. And so I'm going to draw that, and I'm going to label that E2. Now notice a few things about that sketch, or I noticed a few things about that sketch. Well, I'm sure you'll notice the same things about the sketch. Firstly, I drew QE2, the electrical field of Q2, to be somewhat smaller than the electrical fields of E1 and E3. And that's simply because, well, all the charges are the same distance from the field point, but Q2 is smaller magnitude. And so its electrical field will be weaker. Q1, Q3 are larger in magnitude. Their electrical fields will be a bit larger. So I've drawn that fact. I've also drawn the fact that, look, E3 is at an angle of 30 degrees above the horizontal. E1 is at an angle of 30 degrees below the horizontal. So they're symmetric above and below the horizontal. Now, that's important when we start to think about adding up these 3 vectors. So when we add up the 3 vectors, first think about the x component as we add them up. Well, there'll be 2 x components in the direction towards the right, say the positive direction. Those are due to E1 and E3. There'll be 1 component towards the left in the negative x direction. That's due to E2. So that's what's going to happen in the x direction. In the y direction is very interesting. So in the y direction, firstly, there is no y component of E2 because in the horizontal, along the horizontal axis. So there's no y component from E2. Now, E1 and E3 do have y components, but if you look at how they're arranged, because the symmetry of how they're arranged, the y component of E3 upwards is exactly balanced by the y component of E1 downwards. And so although E1 and E3 have y components, those two y components cancel out. And so just from the sketch alone, just from the symmetry alone, we can see that there'll be no y component for the resulting electrical field. There'll only be an x component for the resulting electrical field, and that will determine the magnitude of the resulting electrical field. Let me write that conclusion down. So EY refers to the y component of the resulting electrical field. And we argued that that's going to be 0. EX refers to the x component of the resulting electrical field. And we've said because EY is 0, that is going to be the magnitude of the resulting electrical field. So our calculation will really just amount to summing up, adding up the x components of the 3 individual electrical fields to get the total x component of the resulting electrical field, which is the magnitude of the electrical field. So that's the calculation I'm going to do. I'm going to do it in a couple of steps. The first little step that I'm going to do is actually first just find the magnitudes of E1, E2, E3. Write down the magnitudes of those fields. And then once I've got the magnitudes of those fields, I'm going to use those magnitudes of the fields to determine the x components of each of the fields, the E1x, E2x, E3x, and add those up. And then once I've done that, I've got the resulting x component of the net electrical field. I've got the magnitude of the net electrical field. So let's start by calculating the strength of the electrical field of charge number 2. So that's E2, and by Coulomb's law, it's Coulomb constant, times the magnitude of the charge divided by the square of the distance from the charge. So that's the expression for the electrical field of Q2 at the field point. So we're going to use that equation. And then we're also going to use the equation for the electrical field, the same equation for the electrical field of actually both Q1 and Q3. We can do this in one go, not 2 goes, one calculation, not 2 calculations, because look, Q1 and Q3 are the same charges. Q1 and Q3 are the same distances from the field point. And so they have the same strength electrical fields. Their electrical fields will be the Coulomb constant times the magnitude of their charges divided by, again, the square of the distance. And so I've just got to do these 2 little calculations to find the individual electrical fields at the field point due to the individual charges. So let me go ahead and actually do that calculation. So 9 times 10 to the 9 is the Coulomb constant. Its units are newtons meter squared over Coulomb squared. To save time, I won't write them in. Times the charge. The charge Q2 is, its magnitude is 2 times 10 to the minus 9, is 2 nanocoulombs. And then I've got to divide that by the square of the distance from the charge to the field point. It's 4 centimeters or 0.04 meters. And if you carry out this calculation, I got the value of, I wrote it down, 11.2 kilonewtons per coulomb. So 11,000 newtons per coulomb for the strength of that electrical field. Same calculation for the two other equal sized, equal distance charges. So Coulomb constant, 9 times 10 to the 9. Again, run a test. I'm going to write down the units, but because I'm trying to not take too much time, I won't write down the units. Multiply by the value of the charge. So that's 3 times 10 to the minus 9, 3 nanocoulombs. And then divide by the square of the distance, 4 centimeters, or 0.04 meters. And I also calculated this ahead of time, and I had 16.9 kilonewtons per coulomb. So that's the values of the three individual electrical fields. And that was my first step in the calculation, basically. My second step then is to add up these three fields. And we said we just need to add up the x components of these three fields because the y components of the three fields cancel out exactly. Okay, so the resulting electrical field, E, its magnitude, is going to be equal to the resulting x component of the electrical field because there's no y component. And that's going to be the sum of the three x components of the individual electrical fields. So let me write those down. And I'm going to write them down in the following way. The first one I'm going to write down is the x component of charge Q2. And because that charge was on the horizontal axis, because its electrical field was simply pointing towards the left, the negative x direction, then the x component of the electrical field of charge number 2 is just minus E2. It's in the negative direction, and all its electrical field points in that negative x direction. So that was easy. Now let's do Q1. Well, Q1 pointed to the right and down. So it has a positive x component. So I've got a plus sign here. And the size of that x component is the strength of its electrical field, E1, times the cosine of 30 degrees. So the cosine of 30 degrees will pick out the component of E1 that's in the horizontal, in the positive x direction. So that's E1. And then finally, E2, E3, the x component of E3, well, that's going to be, look, it's got a positive x component, so I've got a plus sign. And the positive x component of E3 is going to be its magnitude, E3, times, again, cosine of 30 degrees. That will pick out the horizontal component. So this is going to be E3 cosine 30 degrees. And so that's our equation based on vector addition, based on superposition for the total electrical field due to these three charges. And now we just got to fill in the numbers for the three electrical fields. And so let me go ahead and just add up these three terms. So E, the net electrical field, which is EX, the net electrical field in the X direction, is going to be the minus E2. So that's minus 11.2 kilonewtons per coulomb, plus E1 times cosine 30 degrees. So E1 is 16.9 kilonewtons per coulomb. Cosine 30 degrees is 0.866. I multiplied those together and I got 14.6 kilonewtons per coulomb. And then I got to do the same thing for the third charge at its contribution, but it's exactly the same contribution as the first charge, Q1. It's the same strength field, and its angle above the horizontal axis is the same as the field of charge 1 below the horizontal axis. So it likewise is 16.9 kilonewtons per coulomb times cosine of 30 degrees. So it's also going to be 14.6 kilonewtons per coulomb. And if I add all these contributions up, I got 18 kilonewtons per coulomb. And so that's the answer to this problem, that the resulting electrical field has a strength of 18 kilonewtons per coulomb, and it's all in the positive x direction. None of it's in the y direction, and that's because of the symmetry. I can draw that. Let me add that electrical field to the sketch. Here it is, in the positive x direction. It's a bit bigger than the individual fields E1 and E3. It's quite a bit bigger than the field E2. And its strength is this 18.0 kilonewtons per coulomb. Anyway, that problem involved Coulomb's law for the electrical fields of point charges. And it involved, more importantly, the superposition principle for the electrical field of several point charges. It also involved a bit of geometry and a bit of symmetry. We made this a relatively simple numerical calculation by recognizing the symmetry of the arrangements of charges. They were laid out on the arc of this circle, and in particular, Q1, Q3 were laid out symmetrically above and below the horizontal axis passing through the circle and the field point.